all up and divide by what? Okay. And I'm doing this, if we're gonna do average value of function, I'm gonna take an average of y values. That seem reasonable? So our average y value would be sum of a bunch of y values and then divided by how many. Great. For a continuous function, there are infinitely many y values that we need to add up. Slide problem. Okay? So how are we going to do that? Surprisingly with an integral. I love it. Okay. So there's a little bit of finagling that we're going to do first, okay, to do that. The first thing to notice, but this would be like our sample, right? We would pick some sample y values or pick some x values, evaluate the function at that, and divide by how many there are. However, in that kind of setup, we usually have this delta x that's a difference between the x values that we picked, right? And we determine delta x by b minus a over a, right? And since n is in this formula, we can solve our delta x equation for n and replace that and get a delta x in there.
That's cool.
Okay? And so we'll do that as follows. We're going to solve. We'll multiply both sides by n and divide by delta x. So we end up with n is b minus a over delta x. Okay, do I need to show up the algebraic steps there? Good. Okay. So, I'm going to rewrite this. Now, this time I'm going to write it in terms of f of x. So I'm going to do f average. And then instead of y's, I'll have like f of x1 and f of x2. So is that going to throw anybody off? Okay. So our f average would equal, what did I say? Would equal f of x1 plus f of x2, and so on, until we have n of those. And then instead of dividing by n, we'll go ahead and use this expression for n, b minus a over delta x. Okay? Now, most of us are not huge fans of fractions. I actually don't mind fractions very much, but I like multiplying fractions much better than multiplying decimals. But if there's one thing we really can't stand, it's fractions in fractions. Right? So, right, that's the only way to make it worse. Right? So let's simplify that so we don't have fractions in fractions. If we do our typical division by fractions, right, we get our copied out flip. So we have our numerator here. And then we multiply, my deltas keep spinning. By the reciprocal of the denominator, so we multiply this time by delta x over b minus a. Okay? And so if we move this to summation notation, our f average is equal to 1 over b minus a, that would stay in the denominator, and then times a sum from I equal 1 to n of f of x of I times delta x. Okay, any questions about that? And that would give us an approximate average, right? And then how do we get to the actual average? Take the limit as n goes to infinity, which turns us to an integral. Okay, so is it okay if I don't write the limit? You gonna be okay there? So our actual F average, so here we should really not have F average equals, rather F average is approximately, right? And then F average is actually gonna equal what happens when we take the limit. But notice that's gonna give us a 1 over B minus A, and then times the integral of f of x dx from A to B. So to try and help you remember this, essentially what we're doing is by doing the integral of f of x dx, we're adding up all the y values, and then we're dividing by how many, which is the length of b to, from b to a. Okay, does that kind of help there? So let's do a couple examples. I only had planned to spend a half a day on this. Can you see why? It doesn't get harder than that. Like that's it. That's all there is for f average. Okay? So there's the best part. It only gets harder if we make the integrals hard, but
we don't need to do that.
we can do this one. I want to do it the other way around. 4x minus. From 0 to 4. I don't know if from is the right preposition there, but good enough. Probably on. Okay. So, f average is equal to 1 over b minus a, so that would be 4 minus 0, times the integral of 0 to 4 of f of x, 4x minus x squared, dx. Okay, now, just real quick before we take the integral, super hard integral. What is this like? What does this graph look like? Like, what should we be expecting? Okay, and from 0 to 4, what part are we at? We're kind of the top, right? And it's at x equals 0, the function is going to be 0. At x equals 4, the function is also going to be 0, right? So, and we're above the x-axis. So we should be looking at something positive here. Does that make sense? And probably not too big. I mean, we got to go up to the. I don't know what the y coordinate, like without doing a little bit more work, I don't know what the y coordinate of the vertex is, but I'm not expecting something too large here, right? Okay. Just, I don't know, manage expectations, do a gut check. Sorry, some of that comes from me not having a calculator a lot, and so like, it's easy to get lost in hand calculations. You all know that, right? And so, you know, if you have these little things that are like gut checks, then sometimes you can be like, well, that seems reasonable, or that's probably not. You know, if I get 200 here, I know I'm probably off. Okay. So, we'll have 1/4 times. We'll go ahead and do our hard integral of 2x squared minus x to the third over 3, and we'll evaluate that from 0 to 4. 2 times 4 squared minus 4 to the third over 3. Oh, that's lovely. And then minus 0 minus 0. Okay. I'm going to at least acknowledge that that's 0. Okay, great. So we've got 32. Minus 64 over 3. Okay, you want a fun by hand trick here? You could use a calculator, right? So at this point, you're welcome to type it in your calculator. Okay, I've got to get a common denominator. which is 3. So this is going to be 3 times 32 over 3, minus now 64 is 2 times 32 over 3. So that's going to end up being 32 over 3. And I didn't have to multiply. Eh? Eh? And so we'd end up with 8/3. And does that seem reasonable? Not too big, positive, so sounds okay. Bless you. Okay. Questions? Pretty easy, right? You want to try one? If we did the x squared minus 4x, by the way, we probably just get negative 8/3. Right, it's sort of a similar shape, but this time 0 to 4 is below the x-axis. Okay, so keep that in mind. Negative answers are fine here. With volumes, that's not good. Area between curves, we should not get negative answers, but when we're doing just the average value of the function, that can be negative if the function is negative part of the time, or most of the time, or all of the time. Okay? Haha, I'm gonna make you do trig. Find the average value. Of f of x equals sine of x on the interval negative pi to pi. I think I know the answers. In my notes I had sine of 4x instead of sine of x. It works anyway. Yeah. Can I just throw this out? Parentheses are your friends. Okay, and what I mean by that is like on a problem like this, if you forget the parentheses, you might end up at the evaluation stage doing 1/2 pi minus cosine of x, when we really should be multiplying. Right, so feel free to use your parentheses, okay? I think I saw that on the test on one of the integration by parts when you got a negative cosine. I think people ended up subtracting, not very many, but do your parentheses. Equals a big donut. By the way, if you think about the graph, what's sine doing from negative pi to pi? It's going through an entire period. Yeah. If I had sine of 4 pi, then between negative pi and pi, it would be going through like 4 periods, and it would still be 0. Still not very exciting. Okay. At least it wasn't longer. I always hate the problems that you like work really hard. You know, you have to do a trig substitution, and you like, it's this long process, and it ends up being 0. And you're just like, I did all that for 0? Give me like pi over 2 or something like that, and I'll feel a little bit more accomplished, but 0's. Okay, so the next question is, if this is the average value of the function, 0 in this case was sine, or 8/3 with the other. One of the questions that mathematicians might ask is, well, can I ever actually equal the average value of the function? Okay, certainly with sine, yes. Okay, and we can guess that probably with the parabola that we would get there, right? And so, but, you know, in general, does that work? Do we equal the average? And the answer is, not surprisingly, yes. And this is, what establishes this in general is called the mean value theorem. Probably should capitalize that. For integrals. If f is continuous, on A to B, then there exists a number c in the interval from A to B, such that f of c equals f average. Which again is equal to 1 over b minus a, b, f of x dx. Equivalently, there we go, make sure I'm spelling right. We could say that b minus a times f of c equals the integral from a to b of f of x dx. Now, if you remember from Calc 1, we had a mean value theorem for derivatives as well, where it's some value c, again, we use that sort of notation. F prime of c was equal to the slope of the secant line between the two endpoints. Okay? And then again, we did this sort of, so how am I getting this equivalently statement? Okay, yeah, I'm just multiplying both sides by b minus a, clearing that fraction. That gives me a b minus a on this side and just 1 over on that side. So, is that making sense? What's kind of cool about this is if you look at it from this perspective, right, what's this integral represent? So this one's the average, right? If I don't have the b minus a anymore, what's the integral from a to b of f of x dx? Area, right? I thought I heard that, right? Area under the curve. So this says this area is equal to, essentially, if I pick the right test point, the area with one rectangle. Okay, there's some point where I can pick that y value and I get the area with one rectangle is the same as the area of the whole thing. Okay, I think that's kind of neat. I will say I don't know of any overly practical use for the mean value theorem, although other than proving more mathematical theorems. Okay, that's what I'm confident about. The mean value theorem is used to prove other theorems, just like the mean value theorem for derivatives. So I will at least admit that. The interesting thing from a mathematics standpoint just is we have a number of theorems where we work really hard to prove that there exists a number c so that something happens, right? And that's all the theorem gives us. It says, yep, there is one. And then we walk away. There exists a solution. That's great. And we're done. And then textbooks like to then throw in the, okay, now find it question. Which, I don't know, as a mathematician annoys me because now we've moved away from the mean value theorem, which just tells me it exists. But that's what the textbook does because, I don't know, that's what they do. So let's do one where we try and find a c, okay? I did two totally different problems over. No, okay, I just had it written down. Okay. So for this one, can we find the c value? Okay. So if we're looking, so let's find c for f of x, 4x minus x squared on the interval that we did, 0 to 4. We could do this for the sine function too, but it's 0. That's not acceptable. It's not worth it. What we do in general, right, is we know from the mean value theorem that there's some number c, so that f of c equals f average, right? And now we're going to invoke the rule that I like to call math by I did that already. We already know f average for this function on that interval, right? It's 8/3. So I need f of c to equal 8/3 for some value of c. Okay, and so that means that 4c minus c squared needs to equal 8/3. And now we just have to solve a quadratic equation. Since I don't have my handy calculator that automatically solves every quadratic equation for me, I'm going to multiply by 3 on both sides and not have to deal with fractions for a while. Okay, so, and then also, since I'm going to do this by hand, I'm going to move these things. I know I need to get everything on one side, right? I guess I could have completed the square, but anyway, I'm going to get everything on one side, and for me it's easier to deal with if the coefficient of the x squared term, or c squared term in this case, is positive. So we're going to go 0 equals 3c squared minus 12c minus 8. Okay, and then I always try and factor, and because I'm teaching factoring in 1010 right now, I think about doing this first, right, doing negative 24. Are there factors of negative 24 that add up to, did I make a mistake?
Shouldn't it be positive?
I did make a mistake, great. Are there factors of 24 that add up to negative 12? Let's see. 2 and 12, nope. 8 and 3, nope. 4 and 6, nope. Nope. Dang. All right, well, it won't factor, so that means we're off to the quadratic formula. Right? Only this time it's not x equals, it's c equals 12 plus or minus square root of 144 minus 4, the 4 that's native to that, times 3 times 8, all over 2 times 3, so 6. All right, 4 times 3 times 8 is 96. And 144 minus 96 would be 50, right? What's that? Am I off? 48? Dang, 48. Okay. 16 is a perfect square factor of 48, so we'll have 4 root 3 over 6, and so, I don't know, I mean, how do you want to break this down? We could do 2 plus or minus 2 root 3 over 3, I mean, that would be one way to simplify that. The real question here, in order to be a value of C for this, is are either of those solutions between 0 and 4? I'm actually pretty sure both of them are, but I'm guessing because I have to approximate here, right? Like I don't know the square root of 3 super well off the top of my head. Okay, I think it's around 1.7, but that's the last digit I know. Anyway, so I think if I do 2 times that divided by 3, I'm not going to be bigger than 2, right? And so I think both of those answers are within 3. And so, yeah, we could say C is approximately, and then use our calculators and give a couple good values. So C is exactly 2 plus 2 root 3 over 3, and 2 minus. So, I mean, we're dealing with a parabola, so is it super surprising that we have 2 answers that work? I mean, it shouldn't be, right? There are 2 places somewhere between 0 and 4 where the y value is equals. And it's probably also not super surprising that it's some crazy irrational number. Okay, good enough? Okay. I want to move on. Is that all right? I'll post homework hopefully today. Anybody planning on getting started today? A couple people, so I'll try and get that up today. I did really good last week at closing the week out, but I didn't think about what needed to come in. And so, like, the class I'm teaching at 1 o'clock, don't know what I'm doing yet.
You know, that's good. That's such a nice feeling. That's what we do too.
I was like, oh man, it's over. I'm not like, sometime this weekend I was like, oh man, I don't even know what I'm teaching on Tuesday. And I didn't spend any time yesterday looking on it. That's how I went. All right. The next topic then, we'll switch to chapter 8. Because we already did chapter 7. And some of you will benefit from doing chapter 7 again, but we still have time. Well, I mean, it's your test score and decide if you're one of those people or not. Right? 2 minutes. You got a decent test score, you could still be like, you know, now I can't do that. So. All right, chapter 8, again, is more applications. That's why we grouped 6 and 8 together. Admittedly, to me, this seems like a math application. I mean, I suppose there could be some realm of science or engineering or something outside of this that you would need to know this. But we're going to do arc length. So how long is a curve? Okay, and so, yeah, I mean, you could see that maybe being used somewhere else if I don't have a regular shape. So, so again, the idea is, call this arc length. I have some sort of random curve that goes from A to B. I meant to kind of do some more shapey things on that. You can draw whatever random curve you want. I wanted to go up and down a couple times this time. And wherever it quits there, I'll B. This time I'm not as interested in the area underneath it, which has applications in and of itself. We'll look at some of those too. But I'd rather like to know how long is this path from A to B, from x equals A to x equals B if I follow the curve. Okay, and unfortunately at this point we have one tool to do that, right? We know the distance formula. Okay, can anybody recite the distance formula? That's okay. If you don't know the distance formula, do you know what you need to know? You need to know the Pythagorean theorem. How many of you know the Pythagorean theorem? That's how we find distance. Okay, so if I have a point here and a point down here, do you know how I find the distance? I do the vertical distance squared, the horizontal distance squared, I add those up and I take the square root. I just did the Pythagorean theorem and found the hypotenuse. Okay, that is the distance formula. But since we're going to need to use sort of the algebraic version, if that's okay, we will at least write it this way. Our distance here is the square root of, I'm going to, normally in an algebra class we do, like x1 minus x2. We're just going to call that a delta x squared, and then delta y squared. Does that work? Okay, so if I want to find the length of this curvy thing, I mean, that obviously isn't going to totally cut it because that gives me a straight distance. And I'm not dealing with a straight line. However, that's what we do. We cut it up into small pieces and approximate it. It's something we know how to do. A straight line. Okay, do you see why I emphasize that at the beginning of the semester? It's how we do like all of our applications. It's how we think about how to do all of our applications here. So, okay, so I'm going to go ahead and draw some dots here, and I'm not going to try and connect them with lines, but essentially I'm going to do Pythagorean theorem or distance formula between each one of those. Okay, and get that. So I'm going to do some of those. Now, in order to make this work really nice and to get a good formula, we're going to alter this just a little bit. We're going to do something a little strange, and we're going to factor delta x squared out of this term. Okay? But how, you say? There's no delta x squared in that term. That's okay. I'm going to factor that out. Okay? The way that I factor that out is I force it. That would give me a 1 in the first term, right? And then for the second term, I would take delta y squared and divide it by delta x squared. Okay, and just verify, if I did the distributive property with my delta x squared here, I would get back delta x squared plus delta y squared, right? Okay, now everybody's starting to crane their necks if they're sitting more than about 2 rows back. So I guess we'll write up on the top of the board. Now we all know how exponents and fractions work. If the top and the bottom are both squared, I can just sort of square the fraction instead of squaring each part individually, right? And so I could rewrite my distance here as the square root of, well, I have this delta x squared times 1 plus, and then I can just make this fraction delta y over delta x. Everybody okay? Okay, that's each one of our little individual segments. So our arc length that I'm going to denote by capital L, okay, is approximately, we can do one other simplification here, sorry, let's do that real quick. I can take the square root of delta x squared. Okay, and delta x is necessarily a positive number, right, so I don't need to worry about a plus or minus there. This is going to end up being the square root of 1 plus delta y over delta x squared times delta x. Okay? Good. And so our approximation is the sum from I equals 1 to n of a whole bunch of these. We get a square root of okay, and our delta y's would be determined by some test points as we subtract some terms. And then if we take the limit as n goes to infinity, and so this becomes, our arc length will be equal along the length of the curve to the square root of 1 plus, now what's, if I go my limit, let's write it out once. I have dy over dx squared. And what's dy dx? It's the derivative of the function. Remember, that's an alternate notation. Okay? And so what we usually will write here is this is a to b of 1 plus f prime of x squared dx. Questions about that?
So are we ever gonna be given f of x?
Oh yeah. Oh yeah. And can I, just like with our rotations and our volumes and stuff, we could maybe do this with a dy. Okay? It's the same thing. It's 1 plus, it would be dx dy, where x is a function of y. Dy. So if I'm given like g of y equals something, where I have a bunch of x, y squareds and, right, so x equals like y squareds and things like that, I can do the same thing. I just do it with the perspective of x, or y instead of x. Okay, let's do this. Find the length of y equals x cubed from x equals 1 to x equals 2. Okay. think I still got 10 minutes. Okay, so anyway, we're still. Great. Well, what we need to do in order to do the arc length is we need to take the derivative of our function. So I need to know what f prime of x is. Well, this is x cubed, so that's, super hard. It's 3x squared. Okay, and then my arc length is the integral from 1 to 2 of the square root of 1 plus 3x squared squared dx. Guess what? That's a really hard integral. Okay, like how are we even going to do that? You could maybe do some kind of really weird trig substitution. This would be really hard. Okay. It turns out that with this sort of configuration, it's really easy to get really hard integrals. Okay, so number one, we're going to focus on, can I get this thing set up? Number two, when I actually want you to find the length, I'm probably going to give you a rather strange function so that when I take the derivative and square it and add one, and then take the square root, it sort of turns out that I actually can do the integral. Okay, does that work? So we're going to have to learn, there's one little trick that we use, we'll probably get to that tomorrow, okay? For one type of them, but if you're seeing some pretty bizarre functions, I'm not trying to make it hard. In fact, I'm actually trying to make it easy, okay? Because here's an easy function, and our integral's really hard, okay? So we're gonna stop there with this problem, okay? And what you may see on an exam is a set up but do not solve kind of question, okay? And then I may do one where I make you solve it. Okay, but again, if I'm handing you sort of a bizarre looking function, it's all about being able to do the integral that is supposed to be. My favorite one was a function that was like f of x equaled an integral of a square root of something minus 1, right? And so that you would take the derivative and the integral would fall out, and then you would square the derivative, and so then the square root was gone. And then you added 1, and so this minus 1 thing fell away, and then you had something pretty simple there. But it looked horrible, and so I'm confident that students looked at it and gave up. It was a multiple choice question, which probably made it worse, because then it was easy to give up on, right? I got a 1 in 4 chance. Okay, let's do one example that we maybe can do, okay? I got 5 minutes here, so I think I can. Don't I? Or, no, that clock's slow. Let's give it a whirl, okay? Here's our function, y equals 1 plus 6 times x to the 3/2. And we're going to do this from x equals 0 to x equals 1. So we're going to run an integral from 0 to 1. Oh, before we do that, sorry. Before we run the integral, let's go ahead and take the derivative. Okay, y prime, f prime, I don't care. But I'm going to have 6 times, so the derivative is 1, the 1 plus is 0, and then I'll have 6 times 3/2 times x to the 1/2. And I just hadn't thought through this part real quick, so that's, okay. So we end up with 9x to the 1/2. Okay. Then we're going to do our arc length equals the integral from 0 to 1 of the square root of 1 plus our derivative squared. dx, outside the square root. Okay, so 9 times the square root of, or 9 times x to the 1/2 squared, just gives me 81x. Okay, how do I integrate that? What would u be? So I heard a quiet u substitution with a question mark, but if we did a u substitution, what would u be? Okay, 1 plus 81x, what would du be? 81 dx. Any problem with that? No, we don't really have the 81, but not a big deal, right? Okay, let's go ahead and change our boundaries, especially since we're kind of short on time here. So when x equals 0, u equals 1, right, because it zeroes out that. When x equals 1, u equals 82. So our new integral is going to be 1 over 81 times the integral from 1 to 82 of the square root of u du. That is a power rule, right? We got u to the 1/2 there essentially, and so not even essentially, we actually in fact have u to the 1/2. Just didn't write it that way. I'll go ahead and write it once that way, just to make sure on your notes you're good. Then as we integrate, we'll get u to the 3/2, then we have to divide by 3/2, so that's the same as multiplying by 2/3. And then we're going to evaluate from 1 to 82. That would give me 2 over 243. That is a fraction that unfortunately does not reduce. And then I will have times 82 to the 3/2 minus 1 to the 3/2, which is 1. As an exact answer, that is the best we can do. If that doesn't satisfy you, insert calculator here. Okay. We'll let that wrap it for today. We'll do a couple more examples tomorrow, and we'll move on to surface area of revolution. Surface area of revolution.